All right, let's get right into it. Today, we're not just going through a mathematical proof. We are cracking a case. I'm talking about a cold case, more than 100 years in the making, all about a mystery that's hidden deep inside the world of numbers. So, welcome to the investigation of the prime number theorem.
So here's our scene of the crime. The prime numbers. You know them, 2, 3, 5, 7, 11, 13, and on and on. They're like the atoms of math, right? The building blocks for every other number. But just look at them. They don't seem to follow any rule. There's no rhythm. It just looks like a chaotic, totally unpredictable mess that goes on forever. But is it?
For centuries, some of the greatest minds in history have stared at this exact sequence and asked that very question. Is all this chaos just an illusion? Could there be some deep, hidden law that's actually calling the shots, telling us where the next prime number is going to show up? Well, that is the mystery we are here to solve.
Okay, meet our prime suspect, the prime number theorem. It makes this incredible claim that if you count the number of primes up to some number x, which we write as pi of x, that count is almost perfectly predicted by this other, much smoother function, Li of x. And for over 100 years, this was just a hunch, a pattern everyone saw, but no one could prove. It was a suspect with a rock-solid alibi.
So the case went completely cold. And the key to cracking it, the one piece of the puzzle that could tie everything together, seemed to lie with this mysterious accomplice, the Riemann zeta function. Now, this is a function that, at first glance, seems to have absolutely nothing to do with simple things like prime numbers.
And this formula, this is the secret connection. On the left, you've got the zeta function of a complex number s, and on the right, you have an expression that is built out of every single prime number in existence. It's a bizarre, almost magical bridge. So to understand the primes, the investigation had to take a sharp turn and focus on this zeta function.
And once they started interrogating the zeta function, the questions got very, very specific. In fact, the whole case stalled on one crucial point, a mystery about where this function hits the value 0.
The entire proof was blocked by this one question. A zero of a function is just an input that makes the output 0. And the big question was this: does the zeta function have any zeros on this one specific critical line where the real part of the input s is exactly 1? I mean, it sounds obscure, but the entire case hinged on the answer.
And then, in 1896, our detective finally enters the story, a brilliant mathematician named Jacques Hadamard. He decides to tackle this case with a classic investigative trick, proof by contradiction. He basically said, look, instead of trying to prove our suspect is innocent, let's do the opposite. Let's assume it's guilty. Let's assume a 0 does exist on that line and just see where that story takes us.
So Hadamard puts his main suspect right there, front and center. His entire investigation is going to start with one single, incredibly bold assumption.
This is it. This is the assumption. Let's just pretend, for a moment, that for some real number t, the zeta function, when you plug in the point 1 plus ti, actually equals 0. We're going to treat this as a temporary truth. Now, let's follow the evidence and see what the consequences are.
And right away, the consequences start piling up. First, it's just a basic mathematical fact. If a function hits 0, its logarithm has to plummet towards negative infinity. And remember that strange formula linking zeta to the primes? Well, because of that, this forces the primes themselves to behave in a really strange, highly organized way. This is our first clue.
And here it is, evidence file number 1. For our assumption to hold true, this sum involving every prime number has to dive to negative infinity. And the only way that can happen is if the cos t log p part is consistently, almost always equal to -1. Our assumption forces the primes into this rigid, predictable pattern. Suddenly, they're not so random anymore.
But this is where Hadamard's genius really shines. See, a good detective doesn't just find one clue and stop. They look at it from every possible angle. And when Hadamard did that, he found a major twist in the story. So he just asked a simple question. Okay, what else has to be true if this bizarre cosine pattern is real? If the primes are really being forced to march in this perfect, orderly formation, what are the other consequences of that? And the answer, believe it or not, comes from really basic trigonometry. If the cosine of some angle is really close to -1, then it's a mathematical certainty that the cosine of twice that angle has to be really close to +1.
So if our first assumption forces the primes into that first pattern, well, then it also unavoidably forces them into this second pattern.
And let me tell you, this second clue, this is the smoking gun. This logical consequence, which follows directly from our first clue, is what is about to break this case wide open.
All right, it's time for the final act. Hadamard takes his two pieces of evidence, the two contradictory patterns forced on the primes by his assumption, and he presents them to the court.
The logic here is just inescapable. If the first pattern meant the logarithm of zeta goes to negative infinity, then this second pattern, where all the cosines are close to positive 1, it implies that the logarithm of zeta, evaluated at a new point, 1 plus 2ti, must shoot off to positive infinity. And if the logarithm goes to positive infinity, that means the function itself has to blow up. It has what we call a pole.
And right here, the entire story just completely falls apart. On the left, we have the logical conclusion from our assumption. The zeta function absolutely must have a pole, an infinity, at the point 1 plus 2ti. But on the right, we have a cold, hard, established mathematical fact. The zeta function only has one pole, anywhere, and it's at the point s equals 1. Our assumption has led us to predict a second pole that we know for a fact simply does not exist.
We've reached a flat-out contradiction, a logical paradox. The story has collapsed on itself. There is no way both of those statements can be true at the same time. It's impossible.
So what do you do? The only way out of this paradox is to go all the way back to the beginning and throw out the one thing that started this whole mess, that initial assumption, the idea that there could be a zero on that critical line. Our guilty suspect, it has been proven to lead to a logical absurdity. It must be false. The suspect is innocent.
And with that, Detective Hadamard rests his case. The suspect has been cleared, and by clearing it, the entire mystery has been solved.
So the verdict is in. Z of 1 plus ti is never equal to 0. There are absolutely no zeros on that critical line. By proving this single negative fact, Hadamard completely demolished the roadblock that had stood for a century. The prime number theorem was finally, officially true. The hidden law governing the primes, it was real all along.
And just think about that for a second. This huge, century-long mystery wasn't solved by finding something new. It was solved by proving that something, a zero on that line, was completely impossible. It really makes you wonder, doesn't it? What other huge secrets are still out there, hidden in the numbers, just waiting to be uncovered? Not by what we can find, but by what we can prove can never ever exist.